denk dat ik dat mag uitdoen.
Van mij mag je dat al.
Ik ga een beetje verder staan. Dames en heren, geachte collega's, ik heet u van harte welkom op de openbare doctoraatverdediging van Thomas Goossens en verklaar de zitting voor geopend. De heer Thomas Goossens is master in ingenieurswetenschappen, richting wiskundige ingenieurstechnieken, van de KU Leuven, en heeft aan de faculteit een proefschrift voorgelegd handelend over Tiny Thin Film Filters from a Different Angle, Correcting Angular Dependency for Spectral Imaging, zoals u met mij kan lezen. In het Nederlands wordt dat vertaald als kleine, dun gelaagde filters vanuit een andere invalshoek. Correctie van hoekafhankelijkheid voor spectrale beeldvorming.
Ja.
En dit tot het verkrijgen van de graad van dokter in de ingenieurswetenschappen. Hij zal het proefschrift nu verdedigen en ik vraag aan de kandidaat eerst een uiteenzetting te geven van ongeveer 45 minuten over zijn werk. Nadien zal er gelegenheid zijn tot het stellen van vragen en het maken van opmerkingen. De heer Thomas Goossens, u heeft het woord.
Dank u wel. Am I understandable like this, or is it too loud? It's fine. Too loud? Good. Okay. So, well, lately we have seen very concerning articles in the news all the time, but nothing trumps what I have seen recently. It's very scary. I was looking at an article about a salad, an innocent-looking salad, but the title was terrifying. They actually found a frog in a salad in a public store where you can buy a salad. So you never want this to happen. And like, why didn't you see the frog in the salad in the first place? Well, it's very similar in color to the surroundings, maybe because it's well camouflaged, who knows? But it looks kind of like salad. Why? Because it has the same color. So color doesn't tell you everything. There are many objects which have the same color or a very similar color, but are still different objects or different materials. For example, we have different kinds of plastics. This is a picture of a fake plant, but just based on the color alone, you wouldn't be able to tell. And an apple might look ordinary to us, but maybe there are small differences we cannot perceive that show, this is a fake image as far as I'm concerned, but that show that there is something that we can see. So the story I want to tell today is why different things can still have the same color and how spectral imaging can help us differentiate between these objects so that we can see the difference, what can go wrong during the spectral imaging process, and how I helped to fix it, at least partially. But for that, I need to start with what light is so that everyone can come along with the story. And maybe the simplest way to perceive light now is something that jiggles. So at a certain frequency, so it goes some quantity goes up and down, but it also propagates through space. And now imagine like something is going up and down, but at the same time it's propagating, then you get this kind of function. So when you see these graphs over there, this is what it represents. It represents light at a certain frequency propagating through space. Now, if you have this kind of function, you can have a distance between the two peaks. This is what we call the wavelength, and which characterizes the specific light you're looking at. Now, the light we have here from the ceiling is not a single wavelength. It's a kind of yellowish white light, just like the sun, and it consists actually of many different wavelengths at the same time, which can be visualized when, for example, using a prism, or when you are looking to a rainbow, where the different wavelengths are refracted at a different angle. So they are all there simultaneously. But the world of wavelengths is very oppressive because they're not all treated equally. Some objects, they reflect more and less like some other wavelengths. For example, here we have a red apple. Why is the apple red? Basically, because it mostly reflects red light. So if the size of this oscillation here represents, it's a representation, how bright the light is that we see, and we have this light coming into the apple, and it is reflected, then we see that the oscillation is much weaker, so not much of the blue light is reflected. If we have red light, which is longer wavelength, so here the oscillation is slower, then you see that almost everything is reflected, so it's only the red light that gets reflected, so that's why the apple looks red to us. Now, these are, of course, only two wavelengths. I just told you there's a whole spectrum of wavelengths at the same time, and we need to represent in some way what happens with the reflection. And this is what we use this kind of curves for, where the x-axis represents the wavelength, so this is one wavelength, this is another wavelength, and the y-axis represents how much of the light is reflected. So you can think of it as if the size of this oscillation depends on the height of the graph. So here, for this wavelength, the shorter wavelength, we see that the oscillation is low, just as the graph is low, and here the graph is higher, and so oscillation is more pronounced. I must say also, but this is not that important for the rest of the talk, that there are many wavelengths we cannot see. There is a small range here that we can perceive, but there is a whole bunch of wavelengths that we cannot see. But I will mainly talk about the range that you see here, the visible wavelengths. My main points will be about that region. Now, you said okay, different objects still can have the same color. Why? Because is a spectrum a color, or is a color a spectrum? Is it the same thing? No. It's a bit more complex. It's actually, the spectrum is a spectrum, like the amount of energy for each wavelength, but our eye, this is quite some oversimplification, it kind of subdivides the region of wavelengths in three regions. So you see here, the colors are not very clear, I see, but this spectrum, consisting of all the wavelengths, is basically sliced in three regions. And that means that we can only perceive the amount of energy in each bin. And it's like having a ruler with only 4 markings. You can only say something is in between 0 and 1 in the ruler, but you cannot say well, in principle you could, but this ruler doesn't tell you where something is. You have to do something special there. So that means that we can have different spectra, like here, they both look different, but still give the same color, the same output. Why? Because it's only the total area under this curve that matters. So if this goes a bit more up and then goes a bit more down, then the total area can stay the same, and then the color, as we perceive it, because that's what our eyes are doing, they're just summing up everything between those regions, we see the same thing. And so we get as long as the low resolution representation is the same, we will see the same color, although the spectrum is different, although it's a different material. And then you say oh, maybe we can solve it with cameras, and the answer is of course yes, but not with any camera. For example, you have the color cameras in your smartphone or your photo, if you have another device, but they could be made more sensitive, but they are made, the color cameras, to mimic our eyes. They also have, just like the eyes, they have different cells to see the different regions, to slice up the region of wavelengths in 3 regions, which are here marked by the blue, red, and the greenish region. And if you look at an image sensor very closely with a microscope, you will see that you also have different pixels with different filters, which mimic what the eye is doing here with these different filters. So they are just made to make aesthetically pleasing pictures for human observers. So I want to show you what this kind of looks like. So this is a nice, colorful photograph, but let's imagine that our eyes only saw this bluish slice of the wavelengths. The others are there, but we only slice and look at the first slice, the bluish slice. Or equivalently, our image sensor only has blue pixels, let's say. Well, then you would see that only where the energy is high in this region, we will see it. And surprise, the bluish flowers here, the brightness here represents the amount of energy in this slice. They are the brightest here, and everything here is black because there is virtually no blue light coming from this region. And the same holds up for the other kinds of slices, the other two slices, where here we only see the green part of the plant, and in this region we only see the red part of the plant. And so that's the idea. Each picture here, although it's black and white, and we're talking about colors, it just represents how much of the light is in this bin, and here in this bin, and here in this bin. And it's these three images, we could say that, well, in digital cameras, these three images are used to produce a color image, and somehow our brains does the same thing, but I don't know much about that, so I will not go. And so spectral imaging is just a natural extension of this idea. Instead of slicing the spectrum up in 3 regions, which makes it us unable to see these small variations, we just slice it up in smaller regions, in more regions. So that means that we have such a black and white image for each region. So we now have a ruler with more markings. We have increased accuracy. So each image here represents just a slice at a different part of the spectrum. That's the idea. And so the hope is then that by doing this, we will be able to perceive these small variations, because only within this slice we see this, and that we can make visible what we previously couldn't see, because these were obscured by our 3 slices. Maybe another way to look at it is, now that we have spectral imaging, that we have for each point in the scene a spectrum. Now you know what a spectrum is. So for example, here we have some avocados, neatly measured by Mr. Andy. And some of them are ripe, some of them are not ripe, but this is the image we see with our eyes, basically, with the 3-slice region. But here we can see at the spectrum there are, at these wavelengths, big differences. And if we just now show the image only at this wavelength, then we see that there are big differences. Some of them light up, some of them are black, basically. And at another wavelength, we don't see the difference. So you can select the right wavelength and then make an image where you see some differences. So you can use it in principle to determine whether your avocado is ripe, apparently. So okay. So now you say like, oh great, I learned something about color and how it works, and like how my eyes work and why different things can have the same color. But so what? What can we do with this kind of technology? And this is the point where I'm glad I can free write on a countless number of applications. For example, there are, just think of any case where there are objects which could have the same color, but you actually want to separate them. For example, in recycling, there might be many different, like I told you already, like many different kinds of plastics, for example, or textiles, which can have different colors, but you nonetheless might want to separate. There's also an example where I think Carolina worked on it with glass and ceramics. They look very similar to us, but you can try to separate them using spectral imaging. Another case is in agriculture. That's very popular at the moment. Because if we look at some plants from above, that's what we would see. We basically see green plants. They all look green to us, but they all have a spectrum. But we don't see all the details of the spectrum. And perhaps, if we can see more details of each spectrum, we can visualize some small variations in the plants, and then bioengineers, not me, can use this to interpret whether the health of the plant is in good state or not. And this is, for example, this is a field of strawberries. It's done by Vito, and in this map, they try to visualize the amount of chlorophyll that is in the plant. That's the chlorophyll index, but I don't know specifically what they do, but they know what to do with it. And that's why they are there. Another fun example is in art, where, well, we see this painting, and the artist tries to make us see what he sees and what he wants you to see, but that doesn't mean there are many things that are hidden to our eye that we can make visible using this spectral camera. And for example, now I'm going through the different slices of wavelengths. You can see that at some wavelengths, some artifacts become more clear, and they can be used apparently to look through the painting sometimes. And this has been recently used in collaboration with IMEC to determine that in Tongerlo there is apparently a painting where John here is painted apparently by Da Vinci, and the spectral camera was used to see whether what the drawings underneath, the pencil drawings were underneath the painting. So this is an actual example. Maybe a totally different example for those interested in epilepsy. If you have, we have blood in our, obviously we have blood in our body, and well, some of the blood carries lots of the oxygen, which comes from your lungs, and some of the blood is coming back to the lungs, which is deprived of oxygen. So there is a, and depending on whether it has lots of oxygen or not, the spectrum is a bit different, although we can basically, we can almost not see it. But here we have a spectrum for, HBO is with oxygen. So with oxygen, we see that there is a different spectrum compared to without oxygen. And to us, here, this is in an open brain surgery, like we don't see a difference, basically, what happens where there's oxygen and there's no oxygen, or less oxygen. But using the spectral camera, we can see these small differences in the spectrum, and we can make visible where the the oxygen supply is happening. And this has been done by a colleague of mine in Montreal, in Canada. And it's not my work. So now you're all convinced that spectral imaging is great and that you want to invest in it and we should do it. And you ask me now, like, how do we do it? Can we do it already? Well, I hinted already. And the technology has been developed already since the 70s. And so there are many designs that are already on the market. But no matter what your design is, somehow you need to slice up the spectrum in wavelengths. Whatever your technology, somehow you need, well, that's debatable, but like you need to, basically you need to slice up the different parts so that you can see different images. And so the idea that I will talk about today is using filters. For example, here, this is an example of a filter where one filter lets through only the blue light and the other filter lets only through red light. And the idea is the same, where we use a filter in front of the image sensor where only a part of the spectrum is let through. And I will explain a little bit because we will need it later. This kind of graph here represents how much of each wavelength is let through. So this is one filter's response, and this is another filter's response, and that's the basic idea. But yeah, how do you make filters which select any wavelength you want? And IMEC has developed technology where they use thin film filters. And you say, thin film filters, I've never heard of that, and most of you may have not, but you certainly have seen a thin film filter. I think everyone has seen an oil spot floating on water, and which is very colorful and rainbow. Nowadays you see lots of, I find it very annoying, you see lots of people with glasses, computer glasses, and every time they talk to you, you see like a bluish reflection, and that's because they have a thin film filter which selectively reflects the blue light, and that's apparently they believe that will make them sleep better. So yeah, but how does it work? This is perhaps the most complicated part of the whole thing, so I will go through it slowly. So remember that I said that light is something that goes up and down, basically. That's the way we will model it now. It's something that jiggles, and we model it, and we have oil floating on top of water. Well, let's ignore the ground for now. So if we have a layer of oil, this is oil. And we will just look at two light rays arriving to simplify the problem for now. So we have one light ray here arriving, and let's say it kind of goes through the oil, reflects here, and comes out here again. There's at least one ray who will do that. But then we have, this is ray 1, and we have a second ray which arrives here, and then reflects already here. It also goes through and then comes out here, but they partially reflect and transmit at each point. That's the idea. Now, here, the two light rays are perfectly in sync. They are going up and down at the same time. But so And here, but the difference is that this ray here travels a longer path than the other ray. So after they come out, they might not be in sync anymore. So they keep going up and down, but this one takes a longer time to get here, so they are not in sync anymore. Or they could be in sync, depends. But here, the rays are overlapping. Now, what does it mean for these light rays to overlap? Well, think of it like if two things are oscillating, like if they're going in opposite direction, pulling basically in the other direction, then they cancel out. It's like having some children's game where people are pulling the rope, equally strong on both sides, nothing happens. So for some wavelengths, the rays add up and cancel out, and they are not reflected at all. They might be transmitted, but they are not reflected. And for some rays, they stay in sync. They go up, and then it's like having the children pull on the same side of the rope, and it goes super easy. So they strengthen each other. And so you can amplify some wavelengths. And then by careful design, you can really select the wavelengths you want. That's the idea. Now, it depends on two things: the thickness of the layer and the angle, and of course the material, but I will not go into that. So if the angle changes, like it comes at a different angle, then the path through this layer changes. So the shift compared to the oscillations changes. If the thickness changes, the path also changes. So that's the basic idea of thin film filters. Now, I already hinted that, in fact, a light ray arrives at the thin film filter, and there are many, many, many reflections, and there are many, many rays that simultaneously overlap. And if you add more and more and more layers, the thing gets more complex. But the idea is always the same. Many rays reflect, many rays overlap, and if you carefully design it, you can make it so that only the wavelengths you want are transmitted. That's the idea. And that's exactly what IMEC has been doing, where they put on each pixel of an image sensor a different thin film layer. So it's not oil, it's some material I am not allowed to share. So, but they put thin film filters on each pixel, and by carefully choosing the thickness of each filter, they can choose which pixel sees which wavelength. So then you can make a sensor which can slice up the spectrum in almost as many slices as you want. And then each pixel here has a different filter response. So this filter, for example, lets through lots of this wavelength, a little bit less of this wavelength, a little bit less, and then nothing anymore. So that's the typical shape of this kind of filters. And to give a rough idea of what it looks like, I can't show the actual picture, but this is a very similar picture. We have these small towers on top of the pixels, and the light enters and then reflects, and you see all these other layers here. It also reflects within those small layers, but that was a bit too much work for PowerPoint. And it's because these filters are so tiny, they are integrated on the pixels. They are like 5 micron wide and several microns thick, maybe. You don't see the difference. Like if you have a sensor with or without filters, like it's the same size, it basically weighs the same thing. So the compact cameras that were already on the market remain compact. And so IMEC has, I think, so far still the smallest spectral camera, a snapshot spectral camera with these kind of spectral filters. So it's because it's so compact that it's usable to put now to put them on drones and fly over crops and fields and easily take them wherever you want to put them. So maybe this is the end of the story. It all sounds great. Cameras work great, and the technology is there. We have applications. I can end here. Alas, luckily there was some job opportunity. Because spectral imaging is not really a plug-and-play process. You can do great things with it, but you need to be very careful how you handle it. And there's a whole chain of events. You have some light, for example, from the ceiling coming and reflecting on a sample, for example, this sponge, and this then reflects to my lens, which focuses the light onto the filters, and then is converted to electricity by the pixel, and et cetera, et cetera. And there are lots of steps where things could go wrong if you're not careful. The simplest example is if you would be measuring outside in the evening with your camera, then you will notice, like have you seen before, the light around you changes, like the red evening sun. it means that the spectrum around you is changing. So your measurement needs to take that into account. So this is, or if a cloud suddenly comes by, then your light from the environment changes. So this is something to take into account. Now, I didn't do much on that, but I looked specifically at how the optics change the behavior of the color filters and how this could produce errors in your measurements and how you can correct for them. So, and there's already a hint because, yeah, light is focused, different angles. I already hinted there is some issue over there. And indeed, when you take one of the cameras, for example here, the IMX SnapScan camera, and I put a sample, let's use this again, it's a nice sample, and I put it at different positions in front of the camera. It's like you're sitting there, and I hold the object at different positions. You don't expect any difference, basically. Like, the spectrum should stay the same if you calibrate your camera correctly, and no matter where I hold it, the color shouldn't change. That's at least what you want. But instead, what I see, depending on which lens I use, the spectrum is shifted in this case. So depending on where I hold it, the color of this object would change, which might not be what you want because your algorithm might confuse it with another object which has a similar color, for example. That would be annoying. But then again, you might say, like, who cares? Like, is it really that important, this spectral shift? And there are certainly, like, cases where you don't have to care about it. Like, if the variation in shift is much smaller than other variations, then you will be able to differentiate between objects anyway. But one of the main added values of spectral imaging is that you are able to visualize the small differences and that you can see them. And because with a color camera, you couldn't see them. But if you introduce measurement errors which obscure these kind of small or make them wrongly measured, then what is the added value of the spectral camera? That's something debatable and depending on the application, of course. But one example application is that I found is made in Wageningen, where they look at the spectrum of a plant, and apparently they can deduce from how much the spectrum reflected from the plant shifts, they can deduce something about the health of the plant. Now, if I hold the plant here, and I hold the plant here, and you say, like, it's healthy, and now it's not healthy, that would be silly. So we will not do that. So I wanted to, like, understand, like, where the shifts come from, and how to predict them, and use that to correct everything. So when you, then of course, when you have some measurement and you can't explain it, or you want to explain it, you have to go to the classic literature and look what people have done before you to solve this issue. And then if I consult the classic thin film filter literature, I find that indeed, like I hinted here, thin film filters are angle dependent. Like, if we have, for example, here one filter and light is coming here at a right angle, then, and this is the filter response, then if the light would be coming at a different angle, here at an angle, then this filter here shifts to the left. So shift means here it filters a different wavelength. It's a different filter, basically. And in the literature, you find neatly an equation that predicts precisely how much it shifts. So that's great, but it's not precisely the problem I had to deal with, because I was using camera lenses which use focused light. And focused light is where the whole cone of light is simultaneously arriving. So you have a whole collection of rays which simultaneously arrive, and each ray is filtered differently. So that's why there are many different filters basically simultaneously operating, and you have to sum up all the contributions. And the problem gets even a bit more complex, because depending on what lens you use, and this is actually the most common case, the cone is not necessarily a nice symmetrical cone. If we have here a lens, and we have this object, then the light is focused here on the sensor like this, a nice cone. But if I put the object here in front of the camera, then the light is focused at a different cone. So this cone here, the distribution of angles is different. So for filters who are not nicely in the center of your lens, you need to take into account different angles and make the correction different. So I think with this analogy, we can now understand why we saw the shift. We have the filters. We can think of them basically as our ruler here. And the filters are shifting. But if the filters are shifting, but we don't know they are shifting, then, and we plot them at the wavelengths we thought they were, then it will appear as if the spectrum we measure is shifting. So that's the reason why we see shifted measurements when we have shifted filters. So the goal is to predict how much these filters shift for a given lens, for a pixel at a given position, and correct for it. And the whole strategy during the work was always to go to the simplest possible model that it can explain almost all of the variation in the data. For example, we have here this kind of filter that I showed you. It's not perfect, like you see some weird edges here, but let's just assume it's a perfect rectangular kind of thing. Let's simplify things. There are no special edges, and especially let's assume that it's actually quite wide, so there are many, many reflections, and we can use the classical theory of thin film theory and predict what's going to happen. So these kind of simplifications you do, and you try to start with the simplest possible explanation. But something that I learned is that even when you have the simplest possible model, simplest possible set of assumptions, that doesn't mean that the equation you get from it has a simple form. It can still be, this is debatable, and some people will find it not, but you can argue that this is a monstrous equation, and this whole equation set, which I will not go into, it predicts how much the filter shifts for a given lens for a given position of the pixel. But something else interesting that I learned during this PG is that actually it's not because the whole equation is a monster that, first of all, the graph that it plots is a monster. This is actually a very nice looking graph. And that with a simple approximation you extract from this monster, you can actually still explain most of the data. And so now we have this simple equation which can basically predict over the whole range that we are interested in how much the filter shifts. And so much of the time that I spent was on reducing this monster of equation using some mathematical techniques to the simplest possible equation that can explain the data. And the advantage of this is, like, here we still have to calculate an integral. There are lots of factors that are not physically significant per se, but here we have a compact equation where each of the factors, this is the size of the aperture, this is the position of the pixel, this is the wavelength of the filter, and this is another property of the filter. It's all physically meaningful, you can all estimate it easily, and you can still use it to predict very well the behavior of the filters. So I reduced these kind of things to make them practically usable. That's the contribution there. And indeed, so now we have this graph of shifted measurements, and if we now take each of these data points, which is plotted at a certain wavelength, we now know this is the wrong wavelength we plotted it, because the filters are shifting. So if we now use this equation to predict for each of these filters what the actual wavelength of the filter was, then when we plot the data again, then all the data aligns again, and then you're corrected, and then the thing doesn't change anymore depending on where you hold it. That's the idea. And the practical implication of this is that it kind of doesn't matter now which lens you use, given that other distortions introduced by lenses are negligible, but as long as you can predict the shift, then you can use whatever lens you want. Previously, this was not necessarily possible in a very practical way. It's always possible because I'm deriving my simple models from existing models. So we could already predict it, but now it's practically usable. And so we can even use lenses with vignetting, etc. Now, the model is being used already by IMEC. It's been being implemented in the software. Apparently, they even convinced some client to pay for implementing it, so that was fun. Then Vito has been using remember They didn't use it for this application with the strawberries, but Stefan Leuven, who couldn't make it today, he told me that he used my model for a specific lens with vignetting to explain what he sees in the data. Then Maarten from Spectricity, apparently, told me that they use my model to see, to have a quick estimation of what they can expect from their device. And then there was also another company which also makes filters, which has been using it for, well, implementing it for certain lenses as well. So this sounds all great. It's like nothing went wrong. It's like fantastic. But there's still a but. While the models do work, they work for some sensors. They work for sensors typically where the filters are spread across multiple pixels. I will not go into the specific details of the different sensors, but there are some sensors where maybe a quick drawing could explain. So imagine that these are the pixels. Then we can either put a filter on one pixel or we can filter on multiple pixels. For the devices where filters are across multiple pixels, the models work fine. It all works. But for the sensor on the right, the snapshot mosaic, for those who are familiar, the model didn't seem to work very well. Which is weird because it's all predicated on established classical thin film theory, and so there might be something wrong with that. So what does it look like? So if we again go to this experiment where we put this filter, now with the small filters, which I call tiny filters, and we illuminate them at different angles, what do we see? Here I show you the graph predicted by classical thin film theory. So this is what you expect from the... And we plot it at 0, 5 degrees, 15 degrees, and 20 degrees. And we see that if you compare, the graph shifts to the left, just as you would expect, like I showed you earlier. However, when you do the actual measurement and calibrate everything, then you see here in color that especially for the large angles, the graph is actually very different from the classical theory prediction. And so this is an important difference that needs to be explained. It's not there are still some... sorry, that was an error. So it seems that, like, if we assume that I did nothing wrong else, that there is something wrong with classical thin film theory when we apply it to this kind of specific case. And the reason is, that's at least what I propose, is we have a thin film filter, and in a thin film filter, the classical assumption is it's very wide, basically infinitely wide. And the light beam that arrives is infinitely wide as well. It's a plane wave that is arriving. So we have many, many rays arriving. They all bounce around many, many, many times. And then at the exit, we have many rays overlapping. Basically, we have an infinite amount of rays overlapping, but that's a technical detail. There are many, many rays overlapping. And this determines the behavior of the filter. Now, I already hinted it, and I already showed you a picture, but these filters, they don't look very wide, right? It's like, okay, this is deceptive, because it might still be a good approximation, but I will show you. But they are kind of tiny. They are 5 micron wide. I can't even show. I think it's like smaller than 10 times smaller than a hair. I'm not sure. But let's zoom in on 1 pixel, and let's look at what light rays do when they arrive at this kind of tiny filter. Let's follow this ray here on the left. So if it arrives at an angle, and we follow it, it goes down, okay, it reflects again, and poof, it's at the side. So it has done only 1, 2 reflections, basically, and then it is lost. And we see that here we have only 1 ray leaving. And there is no other ray that is overlapping with it. So there is no overlapping ray anymore. So the interference behavior, the behavior of the filter, which depended on many, many rays overlapping, it's not valid anymore. And we even have a region where there is no light. And this region is already well known from Dr. Catrissen. But the new thing here that I propose is that the number of reflections is basically limited, and this changes the filter behavior. And then, if we accept this kind of proposition, then we can assume that this is the case, and then look at the consequences of it and compare with experiment when we compute. And this is what I have done. I will not go in all the details of the computation. I will just show you now the result here. Here on the top we see again what I showed you earlier, classical theory versus measurement, where you're at 15 and 20 degrees, where there's a big difference in the filter behavior. But if we use the assumption, and this is actually a calculation for those who know with wave optics, not with the ray model I just showed you, but the idea is the same, we see that the filter behavior is predicted much better than before. Now, who knows, maybe it's a coincidence, but it's at least a first step towards explaining why this is happening, why there's a big discrepancy. The width of the filter, the tiny filter, it matters, and it changes the behavior. So, in summary, again, back to what we are trying to do, is our measurements can be wrong, they can be shifted, and we try to find models to predict what went wrong, and so that we can correct for it. And in the first part, I used classical thin film theory to apply it for ideal lenses and real lenses, and basically extending the theory to make it practically usable. But then I found that for some sensors it didn't work, and I had to extend the idea of thin film filters where the width actually matters. Then, of course, you could say, like, who cares about the tiny filters? Like, it seems to work well for other sensors, so why not use those? There are two main reasons, and I will answer them from the camera designer's perspective, because this is a very early stage result, and I think it's most relevant at this moment for the camera designers, not the users. The first relevancy is in the quality of the filter. And with quality here, I mean how well a single wavelength can be selected and how well other wavelengths can be suppressed. And a typical example, a typical strategy in making filters better is by adding more layers. There's lots of classical theories supporting that, how you can add more layers. Don't take this drawing literally, it's just more layers. The higher your tower becomes, the quicker your rays will bump into the side. Here we still have some reflections, but here we're in the same case that I showed you earlier. There's no more interference and the behavior has changed significantly. So maybe it will not work anymore to increase the number of layers to improve the quality of the spectrum. There will be a trade-off and you will have to find the sweet spot, which I don't know yet. Then a second interesting consequence for camera designers is that the fact that these filters start to behave differently at smaller scales might put some limit, at least, on further miniaturization of these kind of sensors. Why do you want a miniaturization? Well, the problem is, like, if you have a number of pixels and you put different color filters on it, you lose part of the area of the sensor because you have different color filters. And so actually, this is not a real spectral image, but just to convey the idea of a low resolution, you might have lots of spectral samples of this image, but you can hardly see it are flowers. And it's actually, I talked with some people from ILVO that I collaborated with, and I recently heard on some conferences from the EPIC consortium that many of the users, they are interested in actually at the moment more spatial resolution. Because if you have a leaf and you want to find a small spot and detect it, whether it's sick or not, then it's all well that you can measure the spectrum of the whole leaf, but if you cannot see the small dot, then maybe it's not very useful. So if you want to increase the resolution of your image, you need, on the same area, depending on your optical design, you need more pixels. More pixels in the same area means they need to be smaller. If you have smaller pixels, then the filters on top of them, at least in this design, they will also become smaller. And maybe this will put a limit to it in some way. There might be other limitations which become more important first, but at least I show that at the scale we are now already, this effect seems to be significant already. So, is this the end? Well, it's not quite. I propose a theory. I have shown some support for it, but there's still work left to do. For example, we have, although I have some clue what it is, there are some deviations, differences from the measurement and the model that I have no real explanation for, or I cannot well predict at the moment. So this is something that should be looked further at. And also I think it would be useful to develop this kind of models further so we can make some software tool which we can use, because all software tools on the market now for designing thin film filters, they all assume the filters are very wide and there are many, many, many reflections. But this doesn't seem to be the case anymore for this kind of filters. So maybe we can make a new software tool. So maybe now you are completely trained to understand this title, where I have been working with tiny thin film filters. I've been looking at them, how they behave if you illuminate them at different angles. And from the insights and models that I developed there, I could use them to correct for this angular dependency and make these filters more usable for spectral imaging. And so maybe, just maybe, who knows, I know, it would be cool, we will not see this kind of art. Maybe this work will just contribute that we never see this kind of articles anymore, but rather where we can see this kind of articles in the future. So, thank you. Thank you.
So thank you for your very pedagogical or didactical presentation. Enthusiasm was obvious. But now we are coming to the second part of this public defense, which is the questioning part. And the tradition is that I first introduce briefly to you the members of the jury. I will do that in the sequence of questioning. First, I will give the floor to Professor Peter Catrisse, who is online. You see him in front of you. He's from